Also, I got some help from YouTube and no problem, sir.
Okay, good. Then Frank Cardenas, can you share your experience with ETAP software? Abhishek Kumar, can you share your experience with ETAP software and load flow analysis? Sati, can you explain, can you share your experience? Arjit Pasak, can you share your experience with ETAP software as of now? Okay. So, in today's session, I'm going to give some basic introduction about the short circuit analysis. And in the next session, I will use the ETAP software and how we can perform the short circuit analysis. So, in this session, so I'm going to share some basic information about the ETAPs, about the short circuit analysis. So I'm going to share my screen. Let me know once it is visible. Can anyone confirm whether my screen is visible to you?
Yes, sir, we can see.
Yeah, okay, good. So about the short circuit analysis, in the first session, I told that the short circuit in a power system is an unintentional contact between the live conductor or the live conductor to the ground. So during that time, uh, during that time, huge amount of current will flow through the fault path. So So the higher current flow will having some impact in the power system. So in order to isolate the faulty path, normally we are using the protection system. So it including the circuit breaker and CT, relays, etc. So for that, what we have to do, so in order to identify the fault and fault magnitude, so first we have to know what are the types of electrical fault is available in the system. So as we know, we have two type of fault. Uh, the first one is the symmetrical fault and the second one is the unsymmetrical fault. In symmetrical fault, we are having three-phase faults and three-phase to ground faults. In unsymmetrical fault, we are having line to ground, line to line, and double line to ground fault. So these are all the faults are available. These are all classified as mm, the electrical faults in a power system. So during the fault period, the huge amount of current will flow from the source to the fault point. Okay, so some of the problem with respect to that, some I already told about the IEEE standard 399. So in IEEE 399, Chapter 7 is dealing with the short circuit analysis. So in Chapter 7, they have provided the theoretical information about the electrical short circuit is given. So in the previous session, I told that I think Chapter 6 is for the load flow analysis. So all the information relevant to load flow analysis is available in this software. Okay, so the type of fault what I have explained. So those faults are given here. So when you are going through this document, you will get some more information about that. So and also you for before conducting any short circuit analysis, we have to know the machine dynamics. So machine dynamics is about especially the fault current contribution. Okay, so it including the electrical machines like synchronous generators, transformers, then electrical motors. So those electrical equipments we should know about the machine dynamics. So who is the source of the fault current, how the fault current is flowing in the system during the fault, what is the impedance, typical impedance of the particular fault, and how to isolate the faulty portion from the circuit. So what is the protection device used for that purpose, and what is the typical time duration is required to open the circuit breaker. So some of the information about the power system, especially the especially the machine dynamics and the power system protection part. So you should have some basic information. So after that only you have to start working on the short circuit analysis. So now I will go to the fault analysis according to the industry standard. So as I told you earlier, in IEC 60909 is the standard is used for short circuit analysis. On the same time in ANSI, one more standard is used for the short circuit analysis. So the calculation, how the calculation works in IEC and IEEE, that is ANSI, a little bit different, not exactly the same. So you should go through the IEC standard and ANSI standard to get the information about how the standard is calculating the fault current. So that information you should know. And also in IEC there is a factor called C factor. C is a correction factor. That factor is used to calculate the fault current. So one of the typical interview question for power system engineer position is, what is the importance of C factor? So, you please note down this point C factor, and you try to learn about the importance of C factor and how this C factor is used in IEC standard 60909 for calculating the short circuit current. Then in ANSI, IEEE in ANSI, these are all the standards is discussing about the short circuit current. So I am recommending you just to go through IEEE standard 141. So in the 141, some information about calculating the short circuit current is available. Okay, so the now can able to see this table one generic impedance required for the short circuit studies. Okay, so if you have studied the power system analysis subject in your BTech or MTech course in short circuit studies, we might studied that three period in the short circuit current. One is the subtransient period, another one is the transient period, and the third one is the steady state period. So the impedance also the subtransient reactance, transmission reactance, and steady state. So that impedance we should know that. So can able to see here in this one xd double dash is the subtransient reactance and xt dash is the transient reactance and xd is the synchronous reactance. So these reactance is plays an important role in calculating the short circuit current. Yeah, if you remember the electrical machines, especially the alternator, there during the fault time, xt double dash, xt dash, and xt, all the three windings become all the three component become parallel, will be connected parallel during the short circuit. So the net impedance offered by the alternator will be less. So due to that at the time of fault, mm, the fault current, the magnitude of the fault current is high. So that information you have to understand it. And here uh, here they have the standard is given as the the reactance value for the different machines. Okay, so this is for the hydro generators, synchronous motors, induction motor above 1000 hp, 250 hp to about 250 hp to up to 1000 hp. Then these are all 50 hp and above. So for that, what is the typical xt double dash? So that value they have given here. So my suggestion is in the theoretical aspects you have to go through IEEE standard 399 and IEEE 141 for better understanding about the short circuit studies. Then next one is the grounding. So grounding is an important element in the power system. So that grounding is uh, will be a significant in terms of short circuit current. So especially the grounding part, whenever the power system is grounded, the time we have to see whether the grounding is solidly grounded. So in simple words, first we have to know whether the particular system is grounded or not. If it is grounded, then we have to go through the next level, that is whether it is solidly grounded or grounding with impedance or resistance, etc. So in our BTech, we might studied a subject called protection and switchgear. So in that in that we might studied some of the grounding techniques for grounding the transformer as well as the generator neutral point. So that point plays an important role in the short circuit studies, especially with respect to the faults with ground, that is line to ground fault, then double line to ground fault, and three phase to ground fault. So these three fault which involves the ground, so that during that time the fault current through the ground will depends on the system grounding. In a solidly grounded system, the fault current magnitude will be higher in kilo ampere. In a impedance grounding system, the fault current flowing through the ground will be in ampere, let's say 100 ampere or 500 ampere, mostly 500 ampere. So the impedance in the grounding path is used to limit the fault current flowing through the circuit. So that is one of the important thing we need to consider. Then second one is the binding configuration. So in our electrical system, so we are having two type of circuit, no, one is the star circuit and another one is the delta circuit. So the winding configuration of a transformer is one of the important thing we have to accurately model in the software when we are doing the short circuit analysis. Okay, and also the calculation method. So in the calculation method, we can calculate the short circuit current in multiple ways. One of the most used method is per unit based calculation. So I'm requesting everyone to get familiarized with the per unit calculations. Some per unit calculations are for equations are available in the standard itself. If you are not find it all the equation in the standard, then you have to go through some of the power system analysis book and get familiarized with the per unit calculations. So mostly in a small systems we will use the per unit based calculations for the fault current. Okay, so this one will be the typical single line diagram. They have given an example in this standard. So in US they will call this diagram as a one line diagram, but some other people will call this diagram as single line diagram. So mostly here in India, people we will use the terminology called single line diagram. So this is the typical single line diagram. See here, so here we have one generator. It is 15.625 MVA and its substance and reactance xt double dash is 11.2 percentage, and also it having two auxiliary motors, uh, and it is connected to this bus through the distribution or step down transformer. Okay, and also we are having one more transformer that is generated through, this is 12.5 MVA, 12.8 percentage xt double dash. So here we are having two power transformer. Each power transformer is 15,000 kVA or 15 MVA transformer at 8 percentage impedance. This is a transformer 1 and this will be transformer 2. So this transformer is used to step up the voltage, and it is used to export or the powers export the power back to the utility when the generation is high. Suppose whenever the generation is low, this transformer is used as a step down transformer, and the plant will consume the power from the utility. That power is used to feed the motors in the distribution. Okay, so here there is one breaker. This breaker is called as bus coupler. If the breaker is in the same panel, suppose if this breaker is in the different panel, then this breaker is called as a tie breaker. So you try to remember this two terminology: bus coupler breaker and tie breaker. So you have to understand what is the bus coupler breaker and what is the tie breaker. Okay, so the utility bus, that is the high voltage bus, it is 69 kV. So in the 69 kV, it is connected to the utility grid. So at the utility grid, the faulty MVA is the three phase MVA is 1000 MVA, and single phase faulty MVA is 765 MVA, and X by R is, yeah, X by R is 22 for three phase, and X by R is 9.9 for single phase. So, and one of the important parameter in short circuit study is an X by R ratio, that is uh, reactance to resistance ratio. Okay, so this plays an important role with respect to the asymmetrical fault current at the time of fault, and the decaying DC components in the fault. This also one of the typical interview question: what is the importance of X by R ratio in a power system? Okay, you please note it down, and you have to remember what is the importance of X by R ratio in a power system. The first one is that the asymmetrical peak fault current is depends on the X by R ratio. Second one is the DC decaying current is depends on the X by R ratio. So based on this X by R ratio only, the circuit breaker, one of the parameter in circuit breaker is defined. Okay, so and these are all the elements are the distribution network. Okay, so I'm just requesting everyone to go to this single line diagram. Okay, so importantly for the short circuit analysis, we need the data. So what are the data we need for the short circuit study? So here in this 7.7.4 example system data, they have provided the typical data required for the major element in the power system. This is for the generator. So for the generator, we need the voltage, MVA, XT double dash, that is substance and reactance, X by R ratio, and X, then X by R ratio. So 0 is for the zero sequence. So in our electrical power system, we have three type of components. One is the positive sequence components, and another one is the negative sequence components, and the third one is the zero sequence components. So the moment there is a zero in the subscript, then that component is a zero sequence component. Okay, so for doing any short circuit analysis with respect to ground, should have this zero sequence components. If zero sequence is components is not there, then we are not in the position to calculate the fault current with respect to ground. We can able to calculate in the absence of zero sequence component. We can able to calculate only the positive sequence fault current only, not the zero sequence components. Then for the utility, so utility means the power grid. So from the power grid, we need the faulty MVA, then X by R ratio. So this is for the three phase, and these two for the single phase. Single phase to ground, faulty MVA, and single phase to ground, X by R ratio. Then for the overhead line and cable, so for the overhead line and cable, what is the conductor size and conductor length? Conductor length means the particular transmission line or cable length and its impedance. So one R1 X1 is the positive sequence, R2 X2 means negative sequence, R0 X0 means zero sequence. So here they have given only the positive sequence value only. Suppose if we need to calculate the zero sequence, then absolutely we need R0 and X0 values. Then transformer. So for the transformer, absolutely we need the power rating, then primary voltage and secondary voltage, then impedance, then X by R ratio. So the impedance is this Z1 is the positive sequence impedance, and Z0 is the zero sequence impedance, and this X0 by R0, this is the X by R ratio for the zero sequence component. This X1 by R1 is the X by R ratio for the positive sequence components. For the all the transformers, we need this data. Then busway means it's a bus duct. So it is like our cable or transmission lines, but similar to cables and transmission line, busway or bus duct is used to transfer the power from one place to another place. Mostly these type of busways are used in the low voltage system, and some of the locations it is used in the medium voltage system. So if we compare one to one with respect to cable and bus duct, is that the impedance offered by the bus duct is very low compared to the cable. So on bus duct, we are having some different type of requirement and construction. With respect to cable, we are having different type of requirement and construction. Okay, so if you have if you need to know more our information about the bus duct, you just google it, what is bus duct or busway, and you can just figure it, you can just go through some of the bus duct details. Okay, and about the synchronous motor, so we need the motor rating in kVA or HP. Then xt double dash, that is the substance and reactance for the motor, and x by r ratio. Similarly for the induction motor also the same value. Mm, Power rating in HP or kVA, then reactance value, xm means the motor reactance, and x by r ratio. Okay, so here xt double dash. So how the xt double dash is important means, so in a synchronous generator we are having three windings, no? Armature winding, field winding, and damper winding. If you remember the electrical machines, so in a alternator or the synchronous motor, it having three winding, armature winding, field winding, and damper winding. At the time of fault all the three windings become parallel, so the net impedance will be less. So that impedance normally will contribute the higher fault current. So that impedance we are accounting for the fault short circuit studies. Okay. Okay, and also some of the important thing with respect to fault studies are the inertia of the system. Inertia, so in simple words, all the electrical generators and motor having some inertia. So in simple words, what is inertia? Is that in static field, the weight normally we will say in kilogram, weight or mass, normally we will say it is in kilogram. In a dynamic state or rotational state, the weight or mass of the particular equipment or element is called as inertia. So we can understand like this in a simple way. So in a generator and motor, we are having one rotational part that is called as rotor. So the rotor have some mass on it. So whenever the rotor is rotating at the rated speed or synchronous speed, so that time that particular rotor having some inertia. Okay, so if any fault happened in the system, even though if we disconnect the input, the inertia of the rotor will contribute some amount of fault current, some amount of current at the time of fault. Okay, so that is the importance of inertia in a power system. Okay, okay. So one problem nowadays arising with respect to inertia is that is inverter based generation. So nowadays, due to various factors, we are mainly focusing on solar and wind based power generations. These solar and wind systems are not having any rotational elements like rotor. So mostly in solar and wind we are having power electronic based converters. At the time of fault, conventional synchronous generator will contribute some amount of fault current, so that our protected device such as switch gear elements sense the fault and isolate the circuit. But whenever the power electronic based devices largely integrated into the power system, the inertia becomes absence in the inverter based system. So in that time if any fault happened in the system, the fault magnitude contributed by the inertia also become absence. So that is the one of the important concern now. Most of the power grids are facing this kind of issues, especially Australia. So in India, the power grid is very huge and all the grids are interconnected. So at this presently, India is not uh, having any issues with respect to the system inertia, but Australia, it is not like that. So Australian grid is having the limited interconnection. So due to that, with the higher amount of renewable penetration, the inertia become, yeah, significant concerns for them. So due to that, the short circuit ratio of the particular location where the generators or equipments are going to connect, that time the short circuit rating in many locations in the Australian grid is less than 3. So these become an important aspects with respect to the power system operation perspective. Okay, so these are all the things we have to know before conducting the short circuit study. That's all from my end for the today's session. If you have any questions or doubt with respect to short circuit analysis, you please turn on your mic and you can ask me. From the next In the next session, I will take you through the ETAP software, and I will show you how how to perform the short circuit studies in ETAP software. Anyone having some any questions or doubts?